Okay, so our next video then is about mirages, and we will get question number 7 answered in this video here, which really says, what is a mirage and how does it form? Okay, so mirages are kind of complicated, but they are something that we see all the time. They're definitely part of light in nature, and so this is generally what we're talking about here. You're on a road, maybe driving or walking, and you look far in the distance, and you see what looks like water in the road. Okay, so it sort of looks like water, but as you know, you can never quite reach it. There isn't actually water in the road, and the further you drive ahead, the further the water seems to advance in front of you. You can never quite reach it, and maybe you don't think much about it, but that's what we're talking about here. Okay, so in order to sort of address what mirages is then, and hopefully you know what they are now, I need to switch over and tell you a little bit about gases, because the setup for a mirage is something like this. So suppose you have your road here. I wanted a black road here. Suppose I have a road here like this. So here's your road. Okay. And of course, what's above the road on any given day, at least if you're driving somewhere on Earth, which I suspect most of us are, is of course air. Okay. So that's sort of what I'm drawing here. So my setup then is there's going to be the air, and maybe you're here in your car, sort of driving. And, I don't know, I guess, your head's going to be about here, and maybe there's your eyeball like that, and you're sort of looking straight ahead. And yeah, you just sort of see what you see, right? You see the road here, and you see what looks like maybe some water in this region of the road ahead of you here. And what you don't see, but what of course we know exists there, is just a bunch of air. That's, of course, above the road. Okay. But one of the first elements of mirages is to understand here is that the road here, usually on a day where you're seeing a mirage, is hot. The road is warm. Now, roads are warm a lot because they just sort of sit there on the flat ground, just absorbing sunlight all day, right? In fact, that's probably another key thing we should draw in here is I'll sort of draw the sun right here, which of course is illuminating the whole thing, okay? Something like that. And so roads tend to usually be warm just because of this region. They're sitting here just on the flat ground, and they're just baked in sunlight all day. Maybe they're shaded, maybe they're not, but they're sort of warm anyway. So with that, knowing that a room is warm now, let me switch over and tell you about what happens to gases when they get warm. And of course, the gas that I'm going to be talking about here is the air, okay? Because there's air here, which is a gas, all above this sort of hot road. Okay, so off we go then. So I think I showed you this before. This is a gas simulator that we can run on the computer here. So I'll do a couple things here. Let me pump a little gas into this chamber here by just giving this a little squeeze like that. So there's some gas molecules coming out. And I'll make the chamber a little bit smaller here so I can sort of make my point. Okay. And so what will happen, of course, is the air molecules just start bouncing around. And they're sort of constrained to this container here, which doesn't quite translate to our road. Our road was back over here with the car on it. So here would be the gas molecules. Here's maybe the bottom of the container, but of course the gas molecules are free to escape wherever they want. They're not bound into the container the way they are here, but okay, it's sort of the best I can do at the moment, okay? And so what I'll do then is just look at the gas molecules sort of bouncing around in there, purple or blue balls in there. And what I'm going to do is I'm going to start heating the gas molecules up a little bit because we know that the road is hot for mirages. So let me heat these up. And what I'd like you to look at then is what happens to sort of the spacing between the molecules when they get hot. Okay, so here we go. Let's heat it up. Put a fire there. So the molecules start moving faster, and I'll leave it right about here. And hopefully what you notice is that sort of because they're moving around so much, the spacing between them is a little bit larger than if the gas was colder. So let me cool it off here again. Let me cool it off. So you see that when it gets colder, the gas molecules kind of spend a lot of time near each other. They're not so eager to run away and bounce off each other as violently as before. So maybe let me cool it off even more. And I think maybe if you're looking at this, I'm not sure what a good job I'm doing getting my point across, but the gas molecules tend to be a little closer together now when they're colder. And when I heat them up, they tend, I hope, yeah, I think so it's happening. I think it's happening. They tend to stay a little further apart now, okay? And that's sort of what's important to us here is that in this scenario here, they're further apart, and when they cool them off, they get closer together. So I'm going to end this video in just a minute here, but this is our first setup for how Mirages works. Let me give you a little bit of a recap here, okay, of what we just did. So I think what we just did here is we had the following, and we'll just sort of say that if you had a container like this where the bottom of it was hot, then what I'm sort of saying here is that the gas molecules tend to spend most of the time a little farther apart, okay? If you had the same tank over here and it was cooler, then what would happen is the gas molecules here would tend to, they wouldn't be as far apart. Maybe they'd be a little bit closer together. The important part about this here is that when things are farther apart, the medium itself is less dense, okay? And when they're cooler, they're closer together, they're more dense like that. But remember, when we're talking about optics and light here, the density of material has a lot to do with the index of refraction. So if this is like the index of refraction when something's hot, and this is the index of refraction when something's cool, the cooler air and the warmer air have sort of different indices of refraction. And I'll even venture to say that the hotter air, because it's less dense, has a smaller index of refraction than the colder air does. And it's just a simple fact that it's just less dense. Because in the hotter air, the gas molecules are spending more time apart. And in the cooler one, it's more dense. And so the cooler ones are going to have the higher index of refraction. If you want the real extremes of this here, you can think of the cooler one here as ice, and you can think of the less dense one here as, say, maybe, well, not even gas vapor, let's just call it steam, like you see coming out of a coffee pot. This is the extreme case of it here, but you know that ice is cooler and very dense, so it has a higher index of refraction than in the same thing it is steam, which is just hotter and less dense. So if you can just remember that fact, that's the first thing we need to know about how mirages happen, and I'll continue this in the next video.